Now we are ready to learn about functions of complex variables. So, let us start our study with familiar functions of real variables, which if I choose that real variable to be x, we usually use the symbol f of x to denote function of real variable x. It is clear what such functions mean, functions of a real variable mean. If I am given real x axis with some origin, then what a function f of x does is to associate, to assign a given value for any point on the x axis. So, take a point x, it is given a certain value by the function f of x. If we like to represent it graphically, we can choose another axis, y axis, and represent the value of or values of f of x along the y axis. For instance, if for the point x the value of f of x is this, then I could use a point, a dot at x corresponding to that particular value to denote that function at that point. I could continue this exercise for every point and obtain a plot or a curve in general to that represents or that provides values of f of x for every value of x. This is something that we are familiar in the case of function of real variable. So, this is function of real variable. Although I have said function of real variable, it is clear that I am associating a real number with every value on x axis. In that sense, I could more precisely call it a real function of real variable, although we do not usually do that and keep referring to this as function of a real variable. Now, we try to generalize the same idea to the case of complex variables. So, I could consider function of a complex variable f or functions of complex variables z and z bar. I could again try to associate a particular value if I think of this board as the complex plane z, then as I have mentioned, any point on that complex plane could be given a coordinate in terms of z and z bar. A function of z and z bar would then mean giving or associating a complex number with that point z and z bar. Okay. So, f of z comma z bar for us would mean a complex number assigned to the point with coordinates z and z bar. In order to see this in detail, or in order to see the details of a complex function such as this, it is useful for us to choose our familiar real and imaginary axis with the associated Cartesian variables x and y. In which case, a function of this type could be written as in terms of the variables real and imaginary parts, the two variables x and y, as a function of x and y which makes up the real part of this function plus I times another function v of x comma y, which makes up the imaginary part of this function. So that if I know what z and z bar, I also know what x and y are, and putting those values of x and y, I get another complex number, which is what I represent using u and v, whose real and imaginary part I am representing using u and v. Knowing u and v, I know what that complex function is. So that is how we associate a complex number with such a point z comma z bar, and that's what we call, and a function such as this would associate such a complex number with every point on the complex plane. Of course, it is good to ask whether we can represent it graphically. It's a little difficult to do this because well, we can do this, but it's a little difficult because you have a real part as well as an imaginary part to represent. So we can do this, for instance, by choosing one axis, say the z axis for the real part, and plot the real part alone, and choose another graph where we choose v along the z axis and plot the imaginary part alone, but that's not usually done so often. So this is how we write down a complex function in general. It should be now very clear that the set of real functions are a subset of set of complex functions that we have written down here. After all, real axis itself is a part of a complex axis. Okay, so it should be now obvious that the set of real functions that we talked about in the beginning are a subset of the set of complex functions defined here, and it's also not difficult to see that the real axis, which I have represented here using the x axis, itself is a part of the complex plane. Okay. Our next task is to bring in ideas such as continuity of functions and differentiability. Okay, when we consider real functions, we are specially interested in certain type of real functions as we are familiar in physics, such as continuous functions. We are also interested in functions that can be differentiated, whose derivatives are well defined. Such functions are called differentiable functions. Now, coming to the case of complex functions, it is useful to introduce these ideas for complex functions as well. Let us now see how we can introduce these notion of continuous functions and idea of derivatives or differentiation to the case of complex functions. Okay. So to understand this, it is good always to start with the case of real functions. I have a graph of some arbitrary real function that I have displayed here. Let us look at the idea of continuous functions as can be seen from this graph. For real functions, the idea of continuity means the following. If a function f of x is continuous at a point, let us say x, it means that while you approach the point x from two different possible directions, that is from the positive side of the x axis or the negative side of the x axis, the value of the function f of x must remain the same. If that is so, then we call that function continuous. So that is somewhat obvious from the picture, that the value of the function f of x at this point is represented by the point here, and it is clear that as I approach from the positive side of the x axis towards that point, the function value approach this value as you approach from one side of the curve, while when you approach from the negative side of the x axis, the same point, you move along the function curve again towards the same point. In such a case, you say that f of x is continuous at x. In contrast, it is good to look at a function that is not continuous or discontinuous at x. Such a function can also be taken. Its curve could look something like this, for instance. As we would notice that a function represented by such a curve has one value as you approach from the negative side of the x axis, the point x, while approaching the same point from the positive side of the x axis, we get another value. And it appears that there is a break in the function at the point x. That is when you say that function is discontinuous at x. So such a notion of such an idea of continuity or discontinuity can be taken over to the case of complex functions also. Let us see how this can be done. Coming over to the complex plane, as I said, it is difficult to graphically represent the function itself for complex plane for variables that are complex. But to state the idea of continuity or continuous functions itself is not difficult, and the definition goes as follows. It is easier for us to state the definition in terms of the Cartesian variables x and y. So let me do that. Suppose z is a point on the complex plane with its real part x and imaginary part y, then we could say that a function f of z which for now let me choose to write in terms of x and y, is continuous when the function has the same value at the point as you approach that point from any direction in the complex plane. So, to make it clear, it is good to draw a circle of a certain radius, which I call the radius, let me call that radius r, so that approaching this point, which is our point z with real and imaginary coordinates x and y, the function is said to be continuous at z equal to x plus I y if when we approach the point z from any direction or any other points in the neighborhood of z, we get f of z. So, that basically we should get the same value of f of z at z irrespective of which of these directions you choose to approach the point z. So, if this condition is satisfied, then we say that f is continuous. Note that the only difference from the case of a real function or a real function of a real variable is that for a real variable there were only two directions to approach a particular point, but for a complex variable there are many directions and there are infinite directions to approach a certain point. So, when you generalize the idea of continuity, all you have to do is to ensure that irrespective of which direction you approach that point, the function should get the same value. That is when you call it a continuous function at z. Note that the concept of continuity is always given for points. So, in this case it is continuous at z provided this is satisfied for any w.